Welcome back. This lesson is about an odd little molecule called benzene, and you don't need deep understanding of how benzene's put together to do the nomenclature and stuff that we're going to talk about, but let's give you some anyway because you'll need it someday. Benzene is a hydrocarbon, and chemists knew for a fair while that its formula was C6H6, and the question was how it was actually put together. They had ideas like a triangle of carbons and then another triangle of carbons with the corners connected, so a triangular prism sort of shape that they thought might work out, and there was something that looked like a hexagon with a hub in the center of it, and what they eventually settled on is that benzene was a hexagon, or a ring shape, like so. And if you just saw this, probably your first thought would be this is cyclohexane. It's got 6 carbons, they're all in a ring. So if you think of that, that seems all right. But if you try to arrange these atoms around it correctly, C6H6 implies that every carbon has 1 hydrogen on it. So if we hook that up, and if this is a ring, we need all the carbons to be connected so the ring doesn't fall apart. How are we doing so far? We know that every carbon has 4 arms, so to speak, and each of these carbons so far has 3 bonds on it, so we haven't met our bond quota yet. And one of the first really solid ideas for the benzene molecule was, what if it's alternating single and double bonds? Spoiler, this is not right, but they tried this for a while, and it does work reasonably well. It does have the right number of bonds in every direction, and that's certainly something. But studying the benzene molecule, one thing that they knew for sure was that all 6 bonds in a benzene ring are equally strong. And that's not what we should have if it goes single, double, single, double, single, double. We should have 3 stronger bonds and 3 weaker bonds, which is not what they were seeing when they studied it. So this wasn't quite right. And to get at what's going on here, let's try another version of this real fast. Okay, I'm doing the ring again just to make a point. When I did this ring and I had to put in double bonds, I put them in the northwest and southwest and east sides. But really, there's no reason that they couldn't be here, here, and here instead, right? There's nothing special about these 3 bonds that I selected. So why couldn't it be these instead? Well, again, this causes the problem where you have 3 stronger bonds and 3 weaker bonds, which we don't want. It turns out the structure of benzene can be thought of as a blend of these 2 things. Imagine that there's a pair of electrons here that spend half their time in this position and half their time in the other position. They're bouncing between this side and that side. You could almost get away with saying that this is a 1.5 bond because the blue one is there all the time and the orange one is kind of half there. And this bond is a 1.5. The blue bond is there all the time, and then you have an orange bond that's kind of half there. In that kind of arrangement, you could consider each of these bonds to be a 1.5. And so this carbon has 1.5 bonds here, and 1.5 bonds here, and 1 more for the hydrogen. That is a total of 4. And every carbon atom is in that same situation with a 1.5, a 1.5, and a 1. It's deeper than that, and if you keep going in chemistry, you're going to learn about pi bonding and delocalized orbitals, where all 6 of these carbons are pooling 6 electrons and sharing them, and you get a ring-shaped orbital that hovers above this ring. You can get very deep in benzene. We don't mean to do that right now, so I think this is enough detail to serve you for the moment. that these are considered 1.5 bonds, which is an unusual thing that you don't see very often. And sometimes they depict that by putting dotted lines in these positions, so that the solid lines represent a permanent always there bond, and the dotted lines represent a half there bond. That's one way to show it, and the more common way to show it, instead of the dotted lines, is they'll just draw a circle in the middle to represent those mysterious pi bonds that you'll learn about later. A shape like this, a hexagon with a circle inside it, is our standard notation for a benzene ring. And in the workbook, there it is. So when you see something that looks like a nut, that's a benzene molecule. Every one of these corners is a carbon. There are invisible hydrogens sticking out from each of these, and the circle is what tells you we're not talking about cyclohexane here, we're talking about benzene. Fair enough. Let's see if we can get some questions answered with that. So benzene is usually your primary, and so if you just have a hexagon, that's benzene and that's easy. If it has a branch attached to it, then the naming rules we've already taught you work for giving a name. This molecule has a single methyl group attached to it, and so you could call it methyl benzene. Each of the carbons in a benzene has a number to it, so if we wanted to keep our numbers as low as possible, we would probably number the benzene like this. And so if you were thinking we should maybe call this 1-methylbenzene, that's not a bad idea, except when there's one branch, you're automatically going to number that carbon number 1. And so something like this is automatically 1-methylbenzene, and we don't bother putting a 1 in that case. So don't bother numbering this. If you put 1-methylbenzene, you're not wrong, but also people are going to frown at this and say, why did they bother? Of course it's number 1. The rest of these aren't much more difficult. Here we do have 2 methyl groups, and you could number this counterclockwise if you were insane and call this 1,6-methylbenzene, or 1,6-dimethylbenzene, but we don't want that. We want the lowest numbers possible. So here we would go 1,2-dimethylbenzene. Here we have 1, nothing on 2, 1,3-dimethylbenzene. And in this case, 1, 2, 3, 4, 1,4-dimethylbenzene. There are some prefixes they used to use for this, where they would call these cis-dimethylbenzene, orthodimethylbenzene, and trans-dimethylbenzene. Those talk about whether these things are close together at an angle or across from each other. And those are kind of interesting, but the way that we teach now is just with the numbering. So if you see those, it's an oddity that you don't have to worry about. Let's see if we can get in more trouble on the next page. They start getting a little more variety in the branches later on. Okay. So benzene, of course, and what do we have attached to it? We have a methyl group that starts with M, and a 3 is a propyl group that starts with P. Alphabetical order says the M group goes first, so that'll be carbon number 1, and we can call this 1-methyl. Two, 3, 4. This could be 5-propyl, or if we go the short way, which we obviously want to do, it's 3-propyl. And of course our primary is benzene. Not too bad. What else have they got for us? This one's interesting. Remember when I said that benzene is usually our primary? In this case, it's not. If benzene were the primary, then we would have two branches going in different directions coming off it, and that would be really awkward. It is possible, and even necessary sometimes, for another chain, like this thing in green, to be our primary. And if you choose that, that means that the benzene is now a branch. So we're going to think of this thing as 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, counting is hard. This in green is nonane. And on carbon number 4, it has a benzene attached to it. Now, when methane's attached to something, we call it a methyl group. When ethane's attached, we call it an ethyl group. Propane becomes a propyl group. You would really think that benzene attached to something would be a benzyl group. I'm sorry, that's not what they do. A structure like this, where a benzene is attached as a branch, is called a phenyl group. There is an explanation why. It's not really interesting. It just involves people in the English-speaking world were calling this compound benzene, and in France, a chemist whose name escapes me was calling it fen, and from that we got phenyl, and the name stuck. So what we want to say here is that on the 4th carbon there is a phenyl group, and so this is 4-phenyl nonane. Bit annoying, sorry about that, but that's what happens when you get a benzene attached to another chain. Now, here we don't have that problem. Here we just have one branch. It's coming off of benzene, so we can call the benzene our primary. And on here we have a 1, 2, 3, 4, 5, 6, 7 carbon chain. That's heptane, so this will be a heptyl. Don't hear that very often. Heptyl benzene. Do we put a 1 here? Good, why not? Because we don't need it. If there's one branch, it's automatically on carbon number 1. Good. Heptyl benzene. Next one, 2 branches. We have, that's 1 carbon, so that's a methyl group. Here we have 1, 2, 3 carbons, that's a propyl group. M goes first. 1 methyl, because you always put a 1 on your first thing if you have the choice. And if we go the short way, then this is carbon number 2, 1 methyl, 2 propyl. 1 methyl, 2 propyl benzene. And benzene in the middle, and it has a methyl group, and another methyl group. So 1, not on 2, 3, not 4, and 5. This is, first of all, it has 3 methyl groups, so we call it trimethyl benzene. And those methyl groups are on carbons 1, 3, and 5. So 1, 3, 5 trimethyl benzene. If you went counterclockwise, you'd still get 1, 3, 5 trimethyl benzene, so go that way if you like. It won't hurt anything. What do you think for this? If we call this benzene our primary, then we have a branch with an alkane branch going that way and another alkane branch going that way, which has another branch attached to it. That doesn't sound good. Same problem if we go here. This is another one where the only way we're going to get out of it intact is if we call this thing in the middle our primary. This has how many carbons? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons is octane. So that's going to be our primary, and we will call these two things branches attached to it. When benzene is a branch, remember we call it a phenyl group, and we have phenyl groups on carbons 3 and 4. So I'm going to make a mistake here. Tell me what it is. Three,4 phenyl octane. See what's missing? There's 2 phenyl groups, so 3,4 diphenyl octane is what you want. Start with an octane stick. There are 2 phenyl groups on it, and they're on carbons 3 and 4. Fair enough? Seems to be all they have for us on this page. See you in the next one.